Okay, the next in-class problem that we kind of worked through, again, not a sample problem, but something that allows us to think about some of the relevant concepts to this chapter, looked at carbon-11 decay. And we talked about this as counting versus calculating half-lives. So the question was, carbon-11 has a half-life of 20.4 minutes. So what percentage of the original amount will remain after 1.7 hours? Well, we can see that our half-life is in minutes, and the amount of time is 1.7 hours. So if we do a quick calculation here to figure out how many minutes that is, 1.7 hours times there's 60 minutes in every 1 hour, that equals 102 minutes. If we compare this, we can see that this equates to 5 half-lives. So conceptually, it's kind of easy to then think about what percent might remain after 5 half-lives. So I'm going to call this the counting half-lives. So again, there's two ways to approach this problem. The easy way, which is a counting half-lives way, and then a harder way, which involves some more calculation. So we'll walk through what it means. Okay, what do we mean by counting half-lives? Well, let's imagine at the start we have 100%. And let's go through 1 half-life. Well, a half-life means the time it takes for half of your material to disappear. So after 1 half-life, we'd have 50% remaining. So let's take this through 5 half-lives. So after another half-life, so a second half-life, we're going to have 25% remaining. After a third half-life, 12.5%, and I'm assuming you're seeing where this is going. Fourth half-life is going to give us 6.25%. And finally, after the fifth half-life, again meaning 102 minutes, we're going to be left with 3.125%. And I think this is an important skill to teach because I think it's important to be able to ballpark your answers. So again, this one happens to work out exactly, since we have exactly 5 half-lives that remain, we'll have just about 3% of our original material remaining. So you're not always going to have a problem where the amount of time that passed is a whole number integer of your half-life. I hope that made sense. This was a whole number integer of our half-lives. It was 5 times 20.4 minutes. Well, what if I'd asked the question about 105 minutes? We wouldn't be able to do this exact same thing, but we could ballpark and say, well, you know what? We'll definitely be down to 3.125%, and we'd go just a little bit more if we were at, say, 105 minutes. But how much more? Is it going to be less than 3%, or where will we be at? Well, this is why we have a calculating half-lives way of thinking about this. And this kind of introduces us to the fact that there's 2 main equations to use in this chapter, and all of the quantitative nuclear chemistry that we can do involves these 2 equations. The first is the one that we just derived on our last video here, which is the fact that the half-life is equal to 0.693 over K. And again, K is a constant, and in this problem, we can use this equation to give us K. We're given the half-life, but we can use this equation to give us K. So written another way, K equals 0.693 over T1 half, which for this problem, if we go ahead and do the calculation, it's 0.034 per minute. So the other equation, again, that's important to think about for this chapter is the natural log of how much you start with over how much you have at a certain time equals KT. So for this problem, we can start it by saying, you know what, they ask about percentages. Anytime you think about percent, think that means in every 100 grams. So we can kind of set this up to say arbitrarily n sub 0 equals 100 grams. And so n sub t, whatever grams we find, should be the percent remaining. So again, the natural log, we defined n sub 0 as 100 grams. And this way, the answer that we'll get will really be a percent of what we started with. We want to find how much is left at time t. We figured out what our K is, 0.034 per minute. And the time that's passed is 102 minutes. So this equals 3.5. So again, to solve this, we can take e to the both sides, and we're going to get 100 over n sub t. If you take e to the 3.5, that's equal to 32. So n sub t equals 100 over 32, and that equals 3.125%. So we get the same answer for both ways of going about this. And again, this will always work. The counting half-lives way, it's a little bit more involved. It will always give you an answer. I'm sorry, the calculating half-lives. The counting half-lives will only work to give you an answer if you have a whole number integer between the half-life and the time that you're looking at. But I think it's still a good skill to think about because it will allow you to ballpark how many half-lives or where you expect or kind of ballpark an idea for where you think you're going to be left. And we're going to work on a sample problem that examines that in just a minute.